Hello all, today we will discuss section 15.1, and I want to give you a little backdrop of what is happening in this section. In this section we are finding the evaluating the double integrals. So when you evaluate the double integrals, if the function f of xy is bigger than or equal to 0, that means if the function is non-negative, then when you integrate like a to b integral c to d f of xy dy dx, that will give you the volume. That's what is happening in this section, broadly speaking. Now but just like how we approximated the areas using the rectangles, here as well we are going to approximate the volumes using the rectangles, but I'm not going to go into great detail. Here you see first the function f is a function of two variables x and y. So first we are going to integrate with respect to dy, and the domain for y is from c to d. Then whatever we get the answer, that we are going to integrate with respect to x, and the domain for x variable is from a to b. So the domain is always written as ab cross cd. This is the domain of x variable and this is the domain of the y variable, and that's how you would write it. You can also exchange, if the function is continuous and bounded, you can also interchange the limits of integration and write this as f of xy dx dy, where the limits of integration for a is a to b and the limits of integration for y is from c to d. You can also go this way. Or sometimes you can also write it in the short form as integral over the entire domain f of xy, and dx is dy is nothing but this is the length of the rectangle, that is the height of the width of the rectangle, so this is dA. You can also write it like that. If the function is negative, then obviously you get the net sign the volume. In other words, it's not really called as a volume. So I hope you understand this, and in other words, we are also finding the volume of the region z equals f of xy. Here z equals f of xy. Am I on the screen? Yes. And on the grid on the domain AB cross CD. So I want to demonstrate. In the lecture notes online, you can see that I have evaluated volumes of evaluated different double integrals, but I just want to explain a simple example here so that you will be able to follow the lecture notes little easily. So now going back to the problem here, this is what is the problem here. I hope you can view this clearly. Let's see if I can bend it a little more. Okay, and let's see if I can focus a little more for you. So focus. Okay, so here what happens is you are integrating this. So first you are integrating with respect to dy, and then you are integrating with respect to dx. So that means the domain for this problem is going to be 0, 3 cross 1, 2. This is the domain of the x variable, this is the domain of the y variable. First remember that. And you are trying to find the volume of the function z equal to x squared y on this domain. So you're trying to find the volume there. So this is how you would evaluate the integral. So you have integral 0, 3 and integral 1, 2. You have x squared y dy dx. So first let's evaluate the inside integral. So you would get 0 to 3 integral of n dx and integral of 1 to 2 x squared y dy. Okay. Now you want to integrate this with respect to y. So when you're integrating with respect to y, you treat x squared as a constant, so that steps out of the integral sign. So you get 0 to 3 x squared integral 1 to 2 y dy, and you get dx here. Now when you integrate this using the power rule, you get 0 to 3 x squared, and when you integrate it using the power rule, you get y squared over 2, where the limits of integration is from 1 to 2, and you get dx. So this one is going to be now upon substituting the limits, you get 0 to 3 x squared, and upon substituting the limits, you get 1/2 times 2 squared minus 1 squared dx. So that would give you integral 0 to 3 x squared, and 2 squared is 4, 1 squared is 1, so 4 minus 1 is 3, so you get 3 over 2, and 3 over 2 is a constant, so that steps out, so you get 3 over 2 x squared dx. Upon integrating, you get 3 by 2 using the power rule, you get x cubed over 3, and limits of integration is 0 to 3. Now you can see 3 and 3 gets cancelled out, so that means you are left with 1/2 x cubed, where your limits of integration is from 0 to 3. So upon substituting the limits of integration, you get really 3 cubed minus 0 cubed, so that's going to be 27 over 2. That's what is it? Volume. Okay, is this clear? I hope this is clear. Now we will really address a similar problem, but I have changed the limits of integration here. Now first of all, I also want to tell you that we get here the function z equals x squared y is continuous and bounded, bounded on the domain what? And the domain 0 3 across 1 2. Okay. On this domain, so by Fubini's theorem, you will be able to interchange the limits of integrals, the integrals or the order of integration. It is possible. So that's why whether you integrate x first or y first, it really doesn't matter when the function is continuous and bounded, and it is bounded because there are definite numbers here. So let's go ahead and evaluate the integrals here and see. We know the answer. We are expecting 27 over 2. The reason being we got the same thing, we got the same answer here. Okay, let's go ahead and see. So you have 1 to 2 and 0 to 3, and you get x squared y dx dy. So the integration is with respect to x first, so y is treated as constant, so y steps out, so you write 1 to 2 y integral 0 to 3 x squared dx, and you write this as dy. See, upon integration, what you get is you get 1 to 2 y times you get x cubed over 3, where your limits of integration is 0 to 3 and a dy. Now substituting the limits of integration, you get 1 to 2 y, and you get 3 cubed over 3, which is going to be 27 over 3 minus 0 cubed over 3, so that's going to be, the integral is with respect to y. So upon simplification, you get, this is from 1 to 2, right? 1 to 2 y times 27 over 3 dy. Now 27 over 3 is a constant, so it steps outside the integral sign, so you get 27 over 3 times integral y dy, where your limits of integration is from 1 to 2. Now upon integrating using power rule, you get 27 over 3 times y squared over 2, where your limits of integration is from 1 to 2. Upon substituting the limits of integration, you get 1/2 times 2 squared minus 1. So that's going to be 27 over 3 times 1/2 times 2 squared minus 1 squared is 4 minus 1, which is going to be 3. So 3 gets cancelled out, so you get 27 over 2. So when you change the limits of integration, it really did not change the answer. But I mean, I felt this was more easier to do. So which way, integrating with respect to x first and y next was more easier. That's what I thought. Now, would you be able to tell the order of integration by just looking at the problem? Answer is no. It's going to get much complicated as we go. It is going to get a little complicated as we go along the syllabus. So for now, we can stop here. But the theme is this. First of all, when the function is positive or 0, the double integration or double integration or integrating functions of two variables will give you the volume. If the function is continuous and bounded, you can interchange the order of integration. That's the next thing. And when you change the order of integration, you should get the same answer. I hope you understood this. If you have any questions, let me know and we'll go from there. Okay, thank you. Bye bye.